My name is Sasha Furtado and I'm here to welcome you to our virtual expo for this year's capstone project. Our project explores a flame retardant material, also known as a FRM, where we discover the new possibilities of fire retardancy in partnership with Advanced Ceramics Corporation.
Flame retardant materials have the function of preventing the ignition of combustible materials or slowing down the spread of fire. This video displays a fire test that shows the effects of polymeric materials that hold inherent flame retardant properties and a polymer that's been treated with flame retardant materials in comparison to its untreated counterpart. There were two main mechanisms of flame retardancy which were investigated: water release on thermal decomposition, which has the function of diluting local fuel sources, and the endothermic effect, which has the function of consuming the energy released by the fire to locally reduce the temperature and spread.
Our goal for the project was to develop and synthesize a non-toxic FRM, which would be used within the aerospace industry. Our particular application was the flight data recorders, also known as black boxes. However, we hope that this technology will be used within further industries.
We cannot disclose any specific information pertaining to materials used or the synthesis method, as we had signed an NDA for the project. Over the course of the year, we tackled this project by splitting our work into three major categories.
During the literature search, in order to determine potential non-toxic reactants with promising flame retardant ability, we used the test and synthesis method where we selected the most promising product, which we will call product A, and used XRD to confirm the success of the synthesis method, comparing data with another synthesis product, which we will call product B. During the optimization stage, after we confirmed, we moved forward with attempting to synthesize fully pure products A and B, optimizing the synthesis method, and finally measuring the flame retardant mechanisms of actions for product A through TGA and DTA.
What we can tell you about the synthesis method are its benefits, where there's a low pressure process that has a low cost and is easy to perform, with no chemical waste products or requirements for chemical washing, separating, and rinsing.
X-ray diffraction was the main analytical technique used to characterize our samples. This technique generates a diffraction pattern of our samples with a unique fingerprint based off its crystal structures. In the figure to the left, the fingerprint of our purest achieved product A is shown. The results indicated that the material crystallizes as hexagonal plates, which was confirmed by the microstructure of the product, showing plates around 1 micrometer in size, with the image to the right that was taken from SEM. The secondary electron technique was used to generate the surface topological features of the product at a magnification of 5,000 times.
In addition to attempting to synthesize fully pure products A and B, we designed a series of tests in an attempt to optimize the speed and completion of the reaction. Optimizations included changing the synthesis time, the addition of a potential catalytic reagent, and using a mechanical press. Results from two different pressing methods indicated that no discernible change in reaction speed or completion occurred. When including an additional reagent, the reactions yielded an increase in completion for identical test times compared to those with no additional reagent. The addition of such a reagent should be pursued further in future work on similar materials. Changes in synthesis time yielded lower completion rates, which was to be expected. However, it remains unclear as to whether this lower completion is offset by reducing reaction time. The purest products obtained were produced by simply remixing a sample previously completed and running the synthesis a second time.
Because the main objective was to replace currently employed FRMs, the two main criteria used to determine success of a product were the FRM mechanisms in water release and a strong accompanying endothermic effect. Thermogravimetric and differential thermal analysis techniques were used to determine performance benchmarks. The results that came back for our product A were very promising, where we had achieved the goals for demonstrating higher performance than the non-toxic market leader aluminum hydroxide on water release. As demonstrated by the interpolated lines from the start to finish of the decomposition, the mass loss due to water from TGA was determined to be 44%, 9% greater than the market leader. The accompanying endothermic effect, as demonstrated by the large downwards peak, indicates a strong effect in requiring energy to decompose, making this material an excellent candidate for further fire testing to confirm effectiveness and build a case for the application of this product as an FRM.
In conclusion, the project produced meaningful results which can be relayed to Advanced Ceramics Corp and subsequently integrated into their production. These results were obtained for novel materials which are currently not being utilized in any aerospace applications. However, a case should be made for their inclusion due to their excellent performance, biocompatibility, and ease of manufacture relative to currently employed alternatives. Also, the project left a few unanswered questions which can be pursued by the company or future students if desired, which may yield even more optimized products.